Dus beginnen of... All right. Settle down. Hello. Ik ben al dicht aan het lopen. En nu? All right. Hello, everyone. So here. Hello, everyone. I lost my thingy, so I'm going to walk up and down. But I saw it has tracking, so it's very cool. Awesome. So we're going to test that out. My name is William. I'm a Flutter lead and AI domain lead at ICAPS. So what that means is I do things with Flutter and with AI. And today I'm going to combine the two of them. I've worked on apps like the COVID Safe, Ampere, Cybels, Blue Bike, and my passion, if you know me, you know what comes next, is for efficiency, animations, and I like shaders. But today I'm not going to talk about shaders, I'm going to talk about machine learning. And I think the most common thing you hear from machine learning is hard, it's a lot of math, and I'm here to tell you that's not true. It's not hard and it's not, well, it is math, but people a lot smarter than us, or at least a lot smarter than me, wrote packages for it, wrote plugins that does all this nice math and does it for us. So we can take that math and, I don't know where the bin is, but throw it away, we don't need it. The second step is to go to the trash, because we're actually going to need a bit of math. But it's not that hard. You'll need to know things like a pixel. A pixel has 3 values. It's RGB. It's a range between 0 and 255. So if you want to use that for machine learning, you're going to input a value between 0 and 1. So you need to, for each pixel, you need to divide it by 255 and then have 3 inputs for each pixel. But that's most of the complicated stuff that we're going to do today. So you can relax. First, I'm going to talk a little bit about what is machine learning. I'm going to keep it brief. I assume most people know this or that about it, but it's also not that important. You have 3 types of machine learning. You have the supervised learning. Supervised learning is for when you have the data and you know what that data means. So let's say we want to determine a color and what name that color has. So then we have a whole list of RGB values and a whole list of this is blue, this is black, this is light green, this is that. And then, so you have the data and you have the labels. Unsupervised learning is when you have the data, but you don't have the labels. And an example of that is anomaly detection, let's say. So for example, we're looking at our server and we're seeing our server memory usage like this, and then it goes down and then it goes back up. We want to detect those things, so you can hard code if it's lower than a certain threshold, then we have an issue. But it might just simmer down at night, so you don't know what value it needs to be. You can use machine learning for that, and then you just input your history. You say, this is all fine data, it was up and running just fine, and then the machine learning algorithm will just determine itself, I see a spike, this was not in my training data, this is not normal, this is an anomaly. And then you can use that for an automated system and have a human look at it. So that's unsupervised. But what if we don't have any data and we don't have any labels? Then we're going to use reinforcement learning. Of course, you'll need something, and for reinforcement learning, you'll need the rule set. A big example is the game of battleships, Zeeslag. You have the rule set, I say a number, it says hit, miss, and you want to defeat the opponent. So that is something we can do with reinforcement learning. I actually did it for my bachelor paper, so if you're ever interested, come find me. But today we're only going to look into supervised learning, even though the others are perfectly capable of running on Flutter as well. And then there's this thing. If you're talking about machine learning, almost all of the time we're talking about neural networks, especially today. They go a lot bigger than this one. This is a very tiny one. But what this is not how it looks, but a visual representation of it. So you have your inputs. Those are the values we give to the model. So this is a model, a neural net, a model, whatever. These are the values we set, and then we have an output, and that's the value we get. For example, for our color determination model, we will have 3 inputs, one red, one blue, one green. And those will have values between 0 and 1. We'll set it, and then these are all calculations, and those are determined by the model itself. And then we'll get an output. If we're talking about colors, we'll have many outputs. That's a classification model. It will have, let's say, 21 outputs. So one for red, one for green, one for blue, one for light green, one for black. Those will be all the outputs, and those will all have values between 0 and 1. And then you just look at the outputs, say which is the biggest. Oh, that's the color it's going to be. And then the middle part is all the math. We're not interested in that. We just say the model, these are the labels, this is the data, figure out how this works. So this is normally what we write, but here it's done automatically. We have no idea. This is when people talk about a black box, is those values, even if you look at them, you're not gonna know, oh, now it's detecting a monkey. No, we have no idea. You can do some special stuff to visualize it, but it's not important most of the time. So I just mentioned classification. That's if we're doing colors. We can do object detection. The most famous one is faces. Where is an image? In this image, where is the person? The camera is doing this exactly right now. Where is the person? Oh, it's there. He's no longer in the center. I have to turn the camera like that. And then the last one, segmentation, is a bit more advanced than object detection. It's looking at every pixel and determining what category that pixel is related to. So if you look at a face, for example, you get a picture of a face, you put it in the model, and out will come the same face, but all black, and then the eyes, for example, will be marked. Those are eyes. You can do a lot with segmentation, and yeah, with all of these, and those are the ones I'm going to talk to you today. So we're actually going to train a classification model tonight, very exciting, if everything goes right. I already trained an object detection and already trained a segmentation model, but the code I will go through and we'll see what fun things we can do with it. And then we're obviously going to implement it into Flutter as well. So that's what we're going to do. We're going to start, of course, with the machine learning model, and we're going to go through 7 steps together. After this, 5 more steps to implement it in Flutter itself, and these are the steps. So first, we're going to install required libraries. Very exciting. I can't wait. And then we're going to load and validate the data set, create a model, train it, evaluate it, look at it ourselves, very important, and then save it so we can use it in an app. So, libraries. Again, very exciting. Those are the libraries. I'm not going to go through them right now. The last one is the most important one for today, because that's what I'm going to use, and then you can see it right here. This is Jupyter Notebook, and Jupyter Notebook is a way of executing code in blocks. So this is here a Python line, this is Python, and between those I've put Markdown so you can actually know what's going on. And if I go through here, for example, this is not going to do anything, but if I run it, only this piece of code ran. Very useful if you're developing, for example, machine learning, and you want to run a specific part of your code multiple times. For example, I've trained a model, but then I had an error in visualizing my history. I'm not going to go through training the whole model again. It can take days sometimes. I just want to keep the results I had previously and then executing only a small part of my code. And this, I'm going to go through this script today, and it's the color recognizer script. So this will be recognizing colors. Yeah, importing, I'm going to write my model and train it in Python. So importing in Python is very easy to read. It's very similar. Sometimes you'll see S is the same as in Dart. Yeah, not important. Step 1, load the dataset. So now we're actually talking about something useful. Sources of datasets. Obviously, if you're working for a company, you can't just download something from the internet and use it. You can do, for example, YOLO has several fun datasets, but there's also a license, which I don't fully trust. So usually I go to Kaggle. Kaggle is an online platform which has a lot of datasets, which has competitions for machine learning, and then you can download those datasets for other means as well. But most of the time, if you're actually doing something new, you will use a custom dataset. What does a dataset look like? This is, for example, a CSV file, which will have 3 values RGB, and then the label, which is the thing we're trying to learn, which we're trying to guess. That will be the category. So, for example, the first one, 255, it's a red. Yeah, we know it's a red color, so that will be the first index. It's red. The second one, 251, it's also going to look very red. The third one, it's also going to look very red. So that's all red. Then the next line is green, and this will have 10,000 lines like this, which will have labels 0, 1, 2, 3, 4, 5, 6, up to 20. And we're going to load this CSV in, and then we're going to pre-process it. Pre-processing is very important. You're not just going to give your model 255. Usually you want to give it a value between 0 and 1 that will bring the best results. So pre-processing this will be divided by 255. That's the difficult math that I've shown you earlier. Sometimes if you don't have enough data or your model is a bit overfitting, you might want to augment it. Augment will mean use existing data, alter it a little bit, and then use that as an input. For example, if you have an image for a chair and you want to detect whether or not that's a chair, you can flip it horizontally. It will still be a chair. If you flip it vertically, it might not be a chair anymore. That's augmentation. And yeah, obviously resizing. If you have your model defined, you will define how many input fields this has. So if you have a model and we're going to say we have an image size of 640 by 640, then you'll have 640 times 640 times 3 inputs, and you'll need to provide all of those inputs every time. So if you have images that are not 640 by 640, those will not fit into the model input. So you're going to resize every image to be 640 by 640. And then pre-processing output, also important. If you just say 0, 1, 2, 3, and you assume that's the output, you're going to have a bad time because, between 19 and 20 is a very small gap, much smaller than between 0 and 1. You might say, no, it's just the 1. But if you think about how the model operates, it uses multiplication a lot. So it will be a lot closer together the bigger the numbers are. So what we're going to do is one-hot encode. That's just a fancy term to say 0 will be 1, 0, 0, 0, 0, 0. 1 will be 0, 1, 0, 0, 0, 0. So all zeros, and then the index. This will be the index of the 1 in the list. And then last is splitting the data. So you can have a long list, but you don't want to use the data it trained on to validate how well it's doing, because it's trained on that data. It knows that data. So if you remember in school, fun times, if you had time to prepare for a test and you saw 1 times 1 is 1, 1 times 2 is 2, and then you had the test, and the test will say 1 times 1 equals how much? yeah, then you're just remembering it. That's not learning multiplication. So the test will be 2 times 2, for example. Then you really have to think. And that's what we're trying to test as well here. So now I'm going to go through those first steps in the code. So very exciting setup, import, drum ruffle. Will it work? It's taking a long time, you can see. Oh, yes, importing works. That was the easy part. Very scary, yeah. The curse of the demo, but it's working fine up until now. And then the first thing you'll see here is configuration and hyperparameters. So what that means is, the number of inputs. I want to say RGB, red, green, blue. So we'll have 3 inputs. And I also put it next in there in comments what those values are. Batch size is, for example, a hyperparameter. That means that if I change those parameters, the training might change a bit. So if it's not working right, we'll change the hyperparameters, and those are the batch size, the learning rate, how many epochs there are, stuff like that. And then I've got a little bit of config. For example, the model version, it's important that we train something, we can run it back. If we make a mistake, we don't lose the first version. And then here below is a little bit of cheating I did, because I don't have the actual data set of 100,000 lines. I didn't go through and mark them one by one. I have a list of all the colors I want to detect and their RGB values. And then later on, we're going to create our data set. This is not something you should do. If you're planning on machine learning, if you're going to generate the labels, then just use that formula to determine the outcome instead of training a model. But I will also show you what the drawbacks are by doing it like this. So right now we're going to train it. I'm quickly going to disable this, and then we'll notice a small issue. And here is the first step that I find important, and that's validating. Validating stuff that you do. It's very important in machine learning, and after each step you will see that I'm validating something. So right now we're loading our data, and then we're going to validate, is the data fine? Can we use it? So what is important when doing stuff like this is that your distribution is fine. So if I look at this list, I can see, for example, gray is very high represented. 14% of all our stuff is gray. But then if I look, and I really have to look over here, yellow, you see that only 0.32% is yellow. So if you're going to train with this data set, it might just always say gray. Why? Because it's going to be right 14.5% of the time. And you have to look at machine learning as something very lazy. If it can find a quick workaround, if it can do something easy, it's going to do that. So it's never going to guess yellow, because it's always going to be incorrect. It's always going to be brown or gray or stuff like that. So what we want to do is we want to use either data augmentation or go back into the real world and take some more pictures. But today we're not going to do that, because why would we? And then here you can see I have yellow, amber, and orange, and I want to generate more values for those. And then if we now run it again, we're going to have to wait another 20 seconds. But then you'll see here that the distribution is much, much better. And now you can also see the power of Jupyter. I don't need to import again. We saved the whole 7 seconds, if I remember correctly. No, I ran it again, so we already lost it, but no worries. And here you can see, before you look at that, the training and validation split as well. Right now I've got 87,000 training samples and 12,500 test samples. I'm more going to do validation with those, but let's ignore the semantics. This is a good representation most of the time you're going to use 10 to 20% for training, for testing and validation. It depends on your results. You can change that where needed. It also depends on your data set. So now we can see gray is still 13%, but we can also see yellow, if I find it again, we're already at 3%. Right, nice. So now it's also going to guess yellow sometimes, and it might be wrong sometimes, and it might be right sometimes. But at least it's going to guess that. Some more configuration needed. This is just, splitting it up, getting the values right, and this is here where we're going to use our training data and put it in a batch, in batches, so that we can train on those. You'll see here the batch size. That's important. That's how many pieces of data the model is going to look at. So you can do a batch size of 1, and then it's going to go through each and every line of your data, or you can increase the batch size, make it faster, so you don't have to wait that long, but it will use more data. We're also going to shuffle our data. Why is that needed? If you have a data set, most often it's going to be, like I mentioned here, first all the reds, then all the greens, then all the blues. It's not good for your model, because then it will first start to guess red on everything, then it will start to guess green on everything, instead of actually learning something. So again, if it's lazy, it's going to start to use workarounds. So that's why we always shuffle it. You'll also see the seed here. The seed is just used for so you can have the same results every time, and it doesn't matter at all what you put there. It just needs to be a value. You can put it to anything you will like. All right, now we have our training batches, and then again, we loaded our data. We're going to validate it. What we're going to validate right now is to see if our labels are correctly interpreted and to the correct data. So if I run this code over here, you can see lime. That's very obviously lime. And then you'll see green. So is this now correct? No, because that's not lime. Oh no, everything failed. Well, no, that's the result of our generating data. Every human will see that this is not lime, but we generated the data using a method, and it will just be checking which color is closest. So we'll see some strange results later on as well. This is not lime. That's what we're trying to automate. So we would put a human in the loop, and he will label everything, and then he will label this correctly. That is not lime. Over here, it's better, light green. That's light green. You look at your distribution, and you validate that it is balanced, and you check, of course, that everything is loaded correctly. If we're talking about, for example, object detection, you're also going to verify that the bounding box in your data is around the face. First time I ran the loading in the data of the object detection, and the face was not here, but it was here. So then I already knew, if I continue with this, it's not going to work. So that's very important. Step 2 is define the model. And this is the hard part. We're now creating a neural network. This is one of the easiest models you'll ever see. We have our input layer, we have our output layer, and we connect them. That's awesome. So how does that look? That looks like this. So these are our RGB values. These are our 21 outputs. And this is a whole lot of math. And this one, you might say that's not an input. That's our bias. It's used inside the model. How it's actually doing it is, for example, the first color is going to take this value, multiply it by minus 2.6, minus 0.26, then plus this value times some value, plus this value times some value, plus this value. That's the difficult maths that we don't care about. We're going to put our input in it. We're going to get an output, and then we're going to say this is right or this is wrong. If we say this is right, it will enforce the correct weights and biases. If it's wrong, it will unenforce or enforce different ones here. So those values will shift every time we learn just a little bit. We're now using a learning rate of 0.1. If I go up here, you'll see we're using a learning rate of 0.1, but I've used values of 0.00001. So it's really slowly learning, and it takes a long time, but that's more often better to get a better result. All right, so create the model, the same code here. So input layer, output layer, connect the two, and we're going to get a model, and we return it. And then the next step is compiling the model. And compiling the model sounds a bit difficult. We're going to choose a loss function, an optimizer, and metrics. Those are all very difficult terms. Optimizer, just Google it. I'm trying to do this. What's a good optimizer? Oh, Adam. Adam is always fun. We're going to use Adam. OK, good. I want to categorize something. What's a good loss function? Well, category cross entropy. What is this? This is difficult maths I don't understand. But we don't need to understand it. That's the beauty. Somebody else wrote it. It's already optimized. It works fine. We're just going to use it. And this here is actually how the loss function and the optimizer work together to get the best output. So here, this is just a 2D representation. This is one variable. This is another variable. And then the value above is the output of a loss function. So how this is calculated, it can be anything. It's Adam that calculates it. So we don't know it's the categorical cross entropy that calculates the values. We don't really care. But what you see is, for example, this has a very high loss. That means it has a bad result. So the loss is how bad or how good the model is. And this value here is very bad. So we want to get away from it. And then if you have this 2D matrix, you'll see that the optimizer will see, oh, we are at this slope. We have a fancy math terms. We're going to go this way. And so we repeat that every training, and then you'll see it slowly goes down, now. And for example here, this is a local optimum. That's very important to avoid. If we have a very low learning rate, it will go into it, and it won't ever get out of it. It will be stuck there, because that's a local optima. That's a local place where it works the best. It has the best output. So you'll need to choose a bit better output, a better learning rate. But if we choose a too high learning rate, it will go here. Then it will go around and around and around and around, but never go in. So how do we solve that? We can do, I don't know if it's on that slide. No. We can do a learning rate. We can change it after a few times. So we can say after 10 times, we're going to lower the learning rate a little bit. And then we're going to lower it again. So then it's going to fast find the global optimum and then go deep into the hole as we would like. You might say, well, this is very easy. I can see it here. Here, this is the best one. Pick this one. As I mentioned, 2 variables. Machine learning, for the face detection, I think we're talking about 2 million variables. I can see 2D, I can see 3D, I can't see 2 million D. If you can see 2 million D, please raise your hand, that would be awesome. But yeah, it's harder than this representation, of course. Don't mind the spelling errors. So we're going to take the input and the output of the data set. We're going to put the input through the model, and we're going to get a prediction. So we're going to compile the model. We're going to run a prediction, and then this is what we get. So this is the color we input. This is the label we input, and these are all the predictions. So you might say, hey, we didn't learn anything, and the output is very bad. Well, yeah, we didn't learn anything yet. But we're just trying to visualize, is this working? Can we put our input into the model? And do we get an output we expect? So what do we expect the first time when it's untrained to be the values all in the same range. So here you can see they're all between 0.02 and 0.06, which is good. This is what we like to see now. Later on, we want to see, for example, green here. Green has to be very high, near to 1, and all the rest needs to be near to 0. So now that we have this verified, we can put it in a callback, and then when we're training the model, every time it went to the whole data set, we can visualize what it's doing right now. Very cool. We're almost there. Training the model. So this is the most important, exciting part. We're actually going to train a model right now. So for this model, I've had 16 of a batch size. So we're going to input 16 data points at the same time. And we're going to use a learning rate of 0.1. And then we're going to do it 10 times with the whole data set. All right, let's go. Right now, you can see it's doing something. Here you can see the loss. Here you can see the loss. And here you can see a metric we defined. That's the mean square error. That's not important how it's calculated, but what is important is that we expect both values to go down. And now you're seeing this value is going down. And every time it went through the whole data set, you'll see here, it's going to predict it, and it's getting better and better. So every time it's more in the green and less in the teal, and all the rest is already 0. So we're going 10 times through the whole data set. Remember, 100,000 colors. 10 times is 1,000,000 times running the model, but it's already done. Awesome. So what did it learn? Well, it's now predicting for this input almost completely green and a little bit of teal. So we're just going to take the highest value here, and we're going to say, yeah, this is green. Let's check the data set. Yeah, it says green, so it learned something. Awesome. That's just in case everything broke. So now that we learned, we're going to check, did we do something good or did we do something bad? And how we can do that is just by taking the loss and then a validation loss and plotting them on an axis. And I'm going to remove this line and make it better. All right, and this is what we get. So what we see here is the validation loss. Those are the points. And then the training loss, that's the red line. So the loss on the training data set went down, and the loss on the validation data set stayed the same. This is bad. Not good model. We did something wrong, and what we did wrong is we used the bad data set. So we're not going to get much better than this. But what we do see is that it's not high, it's not going up, so it's not the worst. This is from last week when I trained the model. What you see here is the validation loss getting higher and higher, and the training accuracy went up, but the training accuracy, the validation accuracy stayed near 0. So this was very bad, and that's called overfitting. So what it did, it remembered what we learned during our class. It remembered 1 times 1 is 1, 1 times 2 is 2, and it learned that out of its head and forgot everything else that is possible. So it's a very bad model. If you say 2 times 2, it will say 2, because it's either 1 or 2. That's what I learned. The rest is not possible. That's what we would want to avoid. This is also not that great, but again, we have a bad data set. If we're going to look through the other trainings I did, you're going to see a much nicer decrease. So if you encounter this, what you do is you get more data. That's never possible almost. So you're going to adjust your hyperparameters, maybe a lower learning rate. You might add more data augmentation and do stuff like that. But then you train your model, and the next step is evaluate it manually. So what you can do is you can go the boring route and just take your test colors and then see what the output is. But we're not doing the boring route today. Today we're using it in Flutter. So right into the presentation, we can say red 255, green and blue 0. What is the output? This is how it looks. And this is 100% red. Yes, success. If we add green, we're going to get yellow. Maybe a little bit of amber, but it's pretty sure that it's yellow. If we're going to add blue, then we'll see white, and it's white. Very awesome. So I now manually verified the model is very good. I can ship it. We're done here. Yeah. No, that was just the happy flow. We're now going to check the unhappy flow. And for example, if I lower this one, we can lower it all the way halfway here. This is no longer white. It's sure that it's white, but this is no longer white. This is pink for me. What happened is our data set has a value for pink and a value for pink. You can see it here. That's not pink. It is pink, but it's not the only pink you have. So what happened was that our data set is bad, and it set for this point, higher than 1 to 8, is going to be white because it's closer to white. So in practice, test it, validate it, and make sure a human made the data set and not just a formula, because you'll get the output of the formula. Some other fun stuff, yeah, this one says gray or indigo. If we lower this, obviously it's going to be gray. If we put less of this, it's going to be purple. And yeah, it says deep purple, that's good. If we lower it more, it's going to be purple. If we're trying to, yeah, this is purple, nice. So we can play around with it. Most of the time it's going to be good. If we're around gray or around white, it might be a little bit funky. But yeah, for example, this one, deep orange, that's pretty good. If you look at it, it's closest to the deep orange and further away from orange itself. All right, awesome. Very important, don't forget to save. If you close everything down and you lose your session, you lose your model and you'll have to retrain it. Now it's just a few seconds, but it can take a few hours to days. So this is important. Usually you'll save as a Keras file nowadays. H5 is deprecated, but it's similar. If you save it as Keras or H5, you can train further, train again. You can also save it as a TF Lite, and then you can use it in your app in Flutter. So I often save both, just in case, so we can always train again if we need it. And you'll also notice, it's not in this one, but you'll notice here that we have callbacks. And one thing I like to put in the callback is saving in between epochs. So you'll see it later on. It's going to save every time we do an epoch, and it's better value than the last one, then we're going to save it. So yeah, some tips. Quality of data, very important. They always say shit in, shit out. You saw it today. So data quality, very important. Data relevance is also important. It's going to use all of the inputs to try and guess the output. If you put RGB in, and then you also put in the time of day, it's going to try to use the time of day to guess the color. But that doesn't matter, except if everyone only puts in black when it's night. But most of the time, it's not going to matter, so that's very important. It will use the time of day to guess the answer, and if you, for any reason, have all the training data be light when it's day and dark when it's night, then it's always going to do that. A fun story about that is wolf or dog. They trained a whole model to guess if a picture contains a dog or a wolf. It was very good. It had a pretty nice accuracy. Then they put it in production, and then they saw a lot of people saying, hey, my dog is marked as a wolf. And then they looked at their training data, and they saw that all of their training data contained wolves in snow and dogs not in snow. So what the model did was not determine, is this a dog or a wolf? It just saw, oh, there's white on this picture. It's going to be a wolf. Again, all of the previous steps, validate is very important. A better approach would then be to segment the dog or the wolf, so you only have that, or just have more data of wolves not being in a slow and dogs being in a slow. So validate after each step. I find that very important. And then the last one, versions are important. If you're going to do this, use virtual environment. This is kind of FVM for Python. The main difference is in Python, everything is global. All your packages are global. So if you train using TensorFlow 2.15, another project that you use TensorFlow will also use 2.15. Why is that important? In our case, because TensorFlow 2.16 gave me errors in Flutter, 2.15 worked. So make sure you're using correct versions. And if you're going to do multiple things with Python, use virtual environment. All right. Now that I bored almost everyone to death, we're actually going to talk about Flutter. Flutter and machine learning together, how difficult will it be? Well, 5 steps. We're going to install all the required libraries. It's just the one, just dflight Flutter. Then we're going to load them all. It's going to be very easy. Then we're going to pre-process our input. That depends on how difficult it was in your model. Then we're going to run inference, which just means predicting it. And then we're going to handle our output, which also depends on how difficult your model is. So here I mentioned version is important. dflight Flutter, the latest version doesn't work for me. The 10.4 works with TensorFlow 2.15. So you kind of have to look at what versions work together. And web is not supported. They say it's because it's implemented per platform, and web uses JavaScript, and it's not working with JavaScript for some reason. There is a dflight for JavaScript, but it's structured differently. So yeah, for dflight Flutter, web's not supported, but there is a package that does support web, so you can use that one if you need it. Desktop requires building libraries. So as you saw before, I'm using Flutter Deck on my macOS. I had to build a library for that. It didn't work for me, and I found it somewhere on GitHub, so you can just download them as well. There is a very useful package, dflight Flutter Helper, which does some very nice things, but it's deprecated and actually doesn't work anymore. So it's very sad. They're talking about implementing it in dflight Flutter itself, but that's not done just yet. Loading the model, very easy. Just say interpreter from asset and then add your dflight file there. Not that difficult. Then pre-process the data. It is important. If you remember, we had our data set with values 25500. We then converted them to values between 0 and 1. You have to do it again here. If you don't do it here, yeah, it's going to give weird results. So it's not that hard to just divide by 255. I think we can all do that. And then we can put it into our model. And that's a bit weird because it's not something how we usually does things in Flutter. You're going to see we're first defining an output, which is a list, which has tensors in it, with a shape that is the same shape as our model. And it's a bit weird. And then we're going to interpreter run and give our input and our output. But then we get the output. Then if we use that output, it will have all the data that we want to see. So then the whole function looks like this. We're going to define our interpreter above somewhere. We're going to use our input divided by 255. Then we're going to use our define our output, run the model, and then we're going to use the result, for example here, to map the probabilities to labels. So that's this method right here. And for state management, I use setState. Some very important things here. Your models need to be lightweight. They are included in your eventual app. This model is very small because it's just an input and an output layer. As I mentioned before, models of 2 million parameters, not that difficult. It's going to be megabytes we're talking about. user privacy and on-device interference. So it's better to use the model on the device for privacy concerns. If you're talking about face recognition or detecting the face, if you're going to upload millions of faces, people are not going to like that. So putting it on the device is much better for privacy concerns, and it's also going to be real time. If we're going to do something to a face or something different that's not a concern privacy-wise, you can do batch inference, so upload multiple images and download them later on. You can do it on a server. Security, right now, if you're going to look at the demo, and we're going to do it later on, I just saved the TF-Lite file, I put it in the code, and I use that TF-Lite file. If your whole company is based on this one machine learning model, and you just shipped it with your app without encrypting it, people are going to decrypt your app bundle and just use your model. So yeah, use encryption if it's important. Then, very important, don't reinvent the wheel. There's so much machine learning already out there. You just use existing stuff, only if you're doing something very custom. And the last one might be the biggest one. Don't use machine learning if you can just use a formula like we did here. This whole presentation could have been one slide. Instead of doing this all, just use this formula. No, that's important. Yeah, you don't need to use machine learning everywhere, and you have to be very vigilant that if someone says, we want to use AI, we want to use machine learning, that you first say, are you sure? I don't think that you should. So now we're going to see some more demos. If everything works as I would like. So we're going to show my screen. I hope. No. Could not find any device, of course. No. No. That's, yeah, this. And then have a little bit of patience. Yes. Yes, awesome. All right, so I'm first going to go and show you how the face detection is trained. So if we look at the file, it's IPYNDB. That's a Jupyter Notebook file. The cool thing is you can actually use this window here, the outline window. It has all your markdown stuff, and it automatically groups them based on the number you had. So first, install required libraries. We did that. The setup, easy. A bit harder to load the data set, but here we're just going to load images from a given folder. You'll see here that my data has images, has train and validation. And here you'll see a lot of images of people. This data set comes from Kaggle. I didn't took these pictures myself and definitely didn't label them. If you're downloading the GitHub, you won't see them there. You'll see a README file that says where I got them from. So then you'll have to download them yourself. Those are already split in a validation and a training data set, so we don't have to do it ourselves. We can just load them. Here you'll see my parameters, and here you'll see the learning rate decay, and then after how many epochs the learning rate should start to decay. Very fancy. You see the image size. It's a smaller image. It's just 96 by 96. The reason for this is how bigger the input, how bigger the model, how longer it will take to run the model. We want to do it live. We want to give the result immediately. We don't want to buffer every time it sees a face. So that's why I opted for a small image size, and then you'll see here it didn't work for 4 times, and then it finally worked just fine. So that's version 0.5. Over here, you'll see how I parse the data set. If I open the data set, you'll see here it's going to be the same file name, but then a .txt file. And then this will be x minus y minus x max and y max. No, I'm wrong. X minus y minus width and height. Those are all already values between 0 and 1. So even for object detection, you also want to be the output values between 0 and 1. So then what does this mean? If you multiply this value with the width, that's where the bounding box starts. We do some maths, and then we sort it, and then we scramble it again. We validate that the data set is loaded correctly. So here you'll see the image being resized to 96. Not yet. You'll see the image loaded and then the bounding box drawn on top of the image. Is this a person? Yes. All right, the data set's loaded. What you will notice is that there's only one person with a bounding box. That's because I decided to do it this way. It depends on how you want to structure your model. So this data set has a lot of multiple persons on one image. I tried with 3 people. The results weren't that great, and it's just for a talk, so I wasn't going to spend weeks on this. So I just say, okay, we're only going to take one person on the image, and for the labels, we're just going to take the biggest person there. Then we're going to create a model, and here you can see that I'm already cheating a little bit. I'm actually starting off with an existing model. Don't mind the terrain. I'm doing some mistakes here and there. This is a custom loss function. Why did I do a custom loss function? I wanted to know how much place there is different than the predicted one. This is not something I wrote. This is what ChatGPT told me I should do. Like I said, the difficult stuff, don't do it yourself. And then here you'll see how many parameters we have. So this has 2 dots, so 2,228,000 trainable parameters. So these are divided by 2, how many calculations that need to happen. So it's a lot. Then we can start predicting because we have a model and it will not be that good. So then we're going to train it to make it good. And here you can see, for example, the checkpoint saving. So it will save every time it has the best value loss. And it will do that after every epoch. And then we're also implementing early stopping, and that will just mean if we find a value that's not better that many times in a row, 5 times in a row, we're just going to stop the training. And this is pretty awesome because you then don't need to take epochs into account. So you can set it to a high value. For example, here it's 64. You can even set it to 1,000. It will stop when it's reached its best results in a while. So then we're training, and you'll see here some result after the 62 epochs. So we saved the whole 2 epochs by stopping early. And then we're going to check our validation over here, our loss. And then you'll see that the loss goes down and that the validation stays near the training loss. So this is a good graph. It would be better if it goes really down, but that's perfectly possible if we try and use a bigger model. But I didn't want to do that. And then these are some manual verifications. You'll see the first one is not that good, but that's why we take multiple. This one is good, this one is good, this one is kind of good. And here we can already see something we don't like. The data set contains more white people than non-white people, and so it might be a bit biased. So that's also something you'll encounter, models that are very biased. Which is not nice. But it does work eventually. So now I'm going to do the actual demo. And we're going to start off with a color recognizer. You've already seen this. It's just the same one, but here it's in a list. Then we're going to do face detection, and now you'll see here it's very fast, there it's a bit slower, but that's because I'm casting twice. But it's immediately. If I now go here and do this, you'll see it detects one person. That's what we want. And now we did all that to start doing fun things like putting on a hat. Awesome. This is why we need machine learning, so we can put on hats on people. Very nice. So then we can go even further. It crashes, don't worry about it. After you close it, it sometimes crashes. If we now see that this is a face, we can actually extract the bounding box. We can use that as an input for a new model, and then we can start to do really crazy stuff called segmentation. So I'm going to open segmentation here, and I've got two versions. I've got a smaller version because it was a bit too slow. But here you can really see the eye segmentation at work. So we have an input image, this one. We add a mask. That's the true value, and this is the predicted value. So this is actually what we're training on to detect eyes. Where are the eyes exactly? All the code is on GitHub. Go through it. It's a bit more extensive. Here you can see a completely custom model. It's a unit, so what it does is it takes your image, it makes it a bit smaller, it makes it a bit smaller, it makes it a bit smaller, then it enlarges it, but then also uses data from that one, and it enlarges it, it uses the very difficult stuff. I don't understand it, ChatGPT does. Let it write it and just use it. And yeah, again, a loss function, sparse categorical, cross entropy, sure, why not? The good thing here is we can use accuracy as well as a metric. So this is the first prediction without training. You can see some very random values, but it does something. Then we train it, and then you'll see the training and validation loss and accuracy. And then you'll see here the validation and training accuracy starts at 1. So that means that 1 epoch was actually enough. It's not that difficult, apparently. And then you'll see some manual verification of a little baby here, but it detects the eyes almost immediately. The data set I use here, also available on Kaggle, uses input images from video, so that's why it's 5 times the same image. That's why it's important that we shuffle, so it doesn't learn the first face, then learns the second face. No, we want to learn all the faces. And then we can save it as TF-Lite, and then we can go really crazy, except for it's no longer connected. So if we go back, no, we can't go back the screen. Device found, yes, it's loading. All right, and now we can do the eye segmentation demo. You'll notice here that I just used 2 dots. Instead of coloring in the whole eye. We could color in the whole eye, but again, it was a little bit too much to do just for this demo. So I just used the center. If you're going to look at the code, it's also pretty extensive. And I'm going to go through the Python code just in a second. But here I've also included some more important data. You can see how long the image conversion takes, how long the image pre-processing takes, just the face detection, then cutting and processing the face, then the eye segmentation and the post-processing. And now, if we have 2 dots, can you guess what we're going to do? It's going to be awesome. We can add a sunglass. And then you can see, if we go side by side, it actually follows. And I can now switch the camera, so I don't need to run. But now I'm a bit too far, so my training set did not account for this. Now we're going to be really close. No, glasses don't work. frame. You'll see here it's a lot more complicated. So we're starting with the image as a camera image, then we convert it to something RGB that we can use. Then we're going to scale it and have the values between 0 and 1. Then we're going to make it a float 32 list, get an input tensor and put it in the right shape. These are some more complicated stuff, but in the end, running the model is again just one line. You just have to get it in the right format first. And if you have the output, you can easily do it times image face. Why there's a first bracket 0. Talking too long, the battery's running out. Yep. All right, apologies. The laptop battery is also running out, so we don't have that much time. It's because the model can run on multiple inputs as once, so that's why we do the 0 here. If you run on multiple, var 5, you'll obviously have to process each output. Here we're going to crop it then, given the face location. Then we're going to resize that copy. Then we're going to pre-process that resizing of the copy for the eye segmentation, put it in. Then we get the eye segmentation output, which will be a long list of values between 0 and 1 again. For the whole image. So every pixel will have a value between 0 or 1. Is this an eye, yes or no? So then we have some code that we're going to find all of the eye segments, put them in lists, find eye regions. All very complicated stuff that I actually didn't need, but then I calculate the biggest regions, take the 2 biggest regions, calculate the center of it, and that's how I got those 2 points. All right, but in summary, those are just the 11, 12 steps you need to do to implement your own custom machine learning in your apps. I don't expect everyone to start working on it tomorrow, but all the code is on GitHub. Feel free to try it out. It's actually pretty awesome if you get something like this working. And yeah, you saw how fast it can be. It's always nice for a user to have some machine learning implemented. Just think about what you're going to implement before using machine learning, and if you need machine learning at all. Are there any questions?